This is Lab 1, Kinematic Design and Beam Alignment. I'm Nathan Isham.
I'm Alan Gay.
I'm Stephanie Wells.
And we all shared in doing all of the work in this lab.
So this is our setup for aligning the laser to an optical rail. We secured an optical rail to the table and had a laser mounted to a post that had X, Y, theta X, and theta Y as degrees of freedom. We were able to align this by adjusting a pinhole at the beginning of the rail and aligning it through the pinhole and moving the pinhole to the end of the rail and doing the same adjusting tip, tilt, and translation. So once the beam was going through the pinhole at both locations, we knew that we were aligned to the rail. We then were able to align or check the levelness of the table by using a pentaprism and a beam splitter. We put a pentaprism so the beam was bent downwards to the table and placed a tray of water, and this tray of water reflected the beam back to the laser, and we were able to see the deviation of the beam from this. We noted that the beam or the pentaprism was a better option for this because it's only dependent on roll.
Go.
For the co-alignment of two lasers, we first ensured the alignment of the red laser using our aperture at a close and far set point. Once the red laser was aligned, we then took the same aperture without moving its height and aligned the green laser along a different optical rail. Once we ensured those two were well aligned, we placed the pentaprism in and had its back reflection go back into the output of the laser. We then put in our beam splitter, and at that point we could try to go to aligning the two lasers. So at our close set point, our 2 degrees of freedom that we could adjust were the roll of the pentaprism and the position of the beam splitter along the axis. These two had the most significant adjustment at this distance. At the far set point, we could adjust the tip and tilt of the beam splitter, because at the close set point they did not have a large enough effect to be able to tell what they were doing. So using those separations, we were able to align the two lasers spatially and have them meet at the target.
So for the alignment of optical components, you put different types of lenses on the lens holder and a height adjustable post holder and a linear translation stage. So you observe 2 reflections from the lens, one from the front surface and the other one from the back surface. So you control the XY translation and tip and tilt of the lens mount until both reflections coincide on the laser output. And to verify the alignment, you move the lens mount along the Z-axis, and then you should still see both reflections to be stationary on the laser output. So for the beam alignment with the microscope, we put the microscope on the kinematic microscope mount, a height adjustable post holder, and a linear translation stage. So we found out that adjusting the X and Y translation allows you to move the beam, while the tip and tilt allows you to move the crosshair. So to align the microscope, you have to center both the beam and the crosshair onto the original target on the wall. So for the second part, after you insert the lens, you find out that only the beam alignment, but not the crosshair, of the final image on the target is changed when the lens is moving in the Z direction. That's because the lens is not centered with the laser, or the microscope is misaligned. Go. So now when we move the lens, you can see that the beam and the crosshair are still well centered on the target on the wall, which means that the beam is well aligned with the microscope.